Thank you, Sefida, for inviting me. It's nice to be here in Leeds and to see some familiar faces as well, which is always a good thing. So yeah, I come from way up there. It's actually not that far away. It's about 4.5 hours by train if things go normal, but today's a strike day, so it wasn't that great. And yeah, this is the main building. The math building is not fancy like that. We are in a temporary building that's going to be replaced by something else in the near future, but it's about 5 minutes that way from there. Here's a more close-up view of the cloisters in the same building that you were seeing on the first picture, and another close-up view of the same thing. So yeah, it's a nice place. These pictures are taken on the sunny day in Glasgow, and pay attention to the singular the. Anyway, I'll talk about, before going into the topic of my talk today, I'll give you a little overview of the types of research I do and also where it originates from. So I'll end on this, I'll end with the thing that we're going to be doing today, but maybe I'll start with something not related, but still I want to give you a full overview. So one of the things I am interested in involves convection, thermocapillary convection, and another involves solidification of fluids, and those two fields I usually think of together. And if you know my past and where I've been at Northwestern University working with Steve Davis for some time, so you can imagine that I got the idea from him. And he was motivated by applications to additive manufacturing and 3D printing. And that's where the combination of these two fields comes from. Essentially, what you're seeing in the top picture, where it says convection, is a large zoomed-in picture of a typical melt pool in these additive manufacturing processes. And you can see that the flow there is convective. You can see the streamlines. And that comes from the change in the large thermal gradients at the surface. The laser heat source is hot, the ambient thermal field is cold, and then that induces a temperature gradient, which then induces a surface tension gradient, and then you get thermocapillary flow within the melt pool. That melt pool itself solidifies really quickly, because when you 3D print stuff or do additive manufacturing to print various things, the machine swipes really fast, and the trajectory traversed determines the geometry of the finished product. And so during that solidification process, you can get various morphological instabilities that are associated with solidifying fluids. And here's the connection to the solidification of fluids and why we've been looking at both of them combined. So that's what has been motivated by my work with the late Stephen Davis. If you haven't heard, he has passed away a few years ago. Other fields that I'm interested in involve non-Newtonian fluids. So this is actually the non-Newtonian twist comes from a consequence of something unusual you're going to see in the experiments that I'm going to be showing you in a few minutes. So you can modify the unusual behavior, the unusual thing, with rheology a little bit, so hence my interest in going into non-Newtonian fluids. And lastly, I'm also interested in flow in porous media and granular flows. But the thing that we're going to be talking about today is those two. We're going to be looking at thin films and associated viscous fingering instabilities. Now those two usually don't come hand in hand. They're usually two separate things. But it so turns out that you can get viscous fingering, like Safman-Taylor-like viscous fingering, in free surface flows, and we're going to be looking at that halfway through the talk. But let me give you some motivations. The motivation behind all of this is slip. Fluids sliding over substrates, special substrates. and how you can make fluids slide over substrates. So nature does it perfectly. The lotus leaf, for example, is a great example of such a slippery surface. Droplets slide freely over the lotus leaf with very little friction, and it's remarkable that they're able to do that, and they're able to do that because of all the little hairs on the leaf. Because of all the hairs, the droplet actually, rather than being in contact with a solid, so with the substrate, it's in fact in contact with air, and that air is in between the hairs. So the droplet slides over air, meaning there's very little friction beneath it, so you have some kind of slip. And people wanted to replicate this in industry in various applications, for example, the windscreens of high-end cars and various pharmaceutical, biotechnology, and maritime applications. So essentially you can manufacture or roughen a surface like this to produce little fake hairs or little fake pillars to trap air in between them and try to make your surface slippery. So all of these, they're small scale examples, but you can also have a larger scale. There's also a larger scale example, which includes the flow of ice sheets. And at least one of you in the audience is going to be familiar with this, or with this slide maybe even. And okay, did I say flow of ice sheets yet or not? I said flow. Okay, let's clarify flow. So, because when I look at ice, like ice cubes in the freezer, they don't flow. They just melt, get smaller, or grow, solidify. They behave like little solids. But if you think of a very large piece of ice, such as all of Antarctica, that's giant, that will be like 2 kilometers of ice in thickness only, and hundreds of kilometers that way and that way. So yeah, you can imagine that under those 2 kilometers of ice, there are going to be tremendous pressure gradients, and those pressure gradients are going to slowly deform their ice or make it flow, kind of like a viscous fluid would. So in case you're not convinced by that, here's a little picture of the Elephant Foot Glacier off the coast of Greenland, which you can compare to a pile of syrup, a puddle of syrup spreading under its own weight. The shape looks pretty, I'm sorry. Sorry about that. The shape of those two things look pretty similar, but the scale is very different. So you can't just watch this ice and see it move. You have to watch there for a year to see appreciable changes, and you have to be far away from it. You have to be on a plane or something. So yeah, there is a similarity, this analogy between the flow of ice and the flow of viscous fluid, but there's a large change in scale. One happens on small scales, and the other happens on large length and time scales. And there are, so I mentioned velocities. So if you look at the ice velocity maps, you'll see that there are large differences between various parts of Antarctica. For example, the red-colored regions, they are flowing at up to 1,000 meters per year, whereas the green-colored regions, they flow a lot slower at just a few meters per year. So there's this giant contrast between the two regions of ice. And the fast-flowing regions of ice, the red ones and the purple and blue, they have a name. They're called ice streams. They're like rivers of ice. And they're very fast-flowing things. And why is it that there's this 2 order of magnitude difference in the velocities between the two? It just so turns out that the answer lies beneath the ice. So if you zoom in to underneath the ice at the ice bed interface, you will see subglacial till, soft subglacial till. Now, what is till? Till is a mixture of water, clay, and subglacial sediment. It's pretty inhomogeneous. There can be patches of it in one place and less of it in another place. So you can't really assess how thick it is, There are some estimates, it's up to maybe a meter. Anyway, that's a very thin layer in comparison to all of the ice, which is 2 kilometers. So just a meter of till and 2 kilometers of ice. Very thin thing. And you can't really tell how much of it there is. And it can be pretty inhomogeneous in different spots. It can have different mixtures of clay and sediment. But the important thing is, despite all those inhomogeneities, despite all that uncertainty underneath the ice, one thing that we do know is that the till serves to lubricate the ice to make it flow faster. And that lubrication causes the formation of the ice streams seen in red and purple and blue in this ice velocity map in the video that we have just been looking at. So now that we've been convinced that ice flows, and we've talked about the velocities, we've talked about what enhances the flow, we can do some modeling to try to understand where all of that comes from. And there are various limits you can focus on. So you can focus on like very shear-driven flows or extensional flows, or various limits you can look at. One thing that they have in common in various limits is that if you depth average all your equations, use your usual lubrication theory, so your fluid mechanical machinery. Now that you know that ice flows like a fluid, you can use all the fluid mechanics that you know to try to model it. So you can do this depth integrated lubrication theory, and in various limits, obtain expressions for ice flux and lubricant flux. Forgetting the rheology for now, just in general, just think in terms of fluxes. Both of these fluxes would have some kind of gravitational spreading terms. Geophysicists would like to call them glaciostatic spreading terms, like we would say hydrostatic. And importantly, there are these viscous coupling terms. And due to these viscous coupling terms, these viscous coupling terms, they are what's causing these very fast flows. You can confine all the shear effectively in the layer of lubricant, and that's embedded in these viscous coupling terms, which then causes these very fast ice flows. You can also do some, you can have lots of ideas by running some small-scale fluid mechanical experiments. And a lot of these come from one of you in the audience. Maybe you've been giving talks here, Sam, about your experiments, but I like to put them in my slides to motivate why it's important to run fluid mechanical experiments, because they give you some kind of idea about how you can test theoretical principles and whether they measure up against your models or not. And there is one important thing that is very difficult to scale glacial processes to lab scales. And another difficulty is generating slip beneath these flows. And generating slip has always been an impediment in the lab. And why is that? And these experiments, the same thing applies to these experiments. In general, in the lab, when you have a viscous fluid in contact with a substrate, like this table, what happens is that substrate, you have to satisfy in the lab the no slip condition at the bottom. But that's not how things work in nature. So for example, these ice sheets, they slide over till, which is also lubricated by water, and that's something that's a bit hard to try to generate in the lab. But there are several ideas. So, for example, we could think about that lotus leaf from the first slide, or one of the first slides. So that lotus leaf slides because of the roughness. The droplets slide over the lotus leaf because of roughness. So we can try to introduce some kind of roughness in the lab. So we can try to use a hydrophobic surface in the lab. But the problem is with such an idea is that you don't get very much slip. So we've tried this. We can run an experiment with a one-side hydrophobic surface coating, and the other side you can have a regular substrate, flow syrup over it. You're not going to see appreciable differences in the velocity. And then you can dig a bit further in the literature and find out why is that, and you'll see that these slip velocities, you can find the associated slip lengths, and you'll see that the sliding is appreciable only on length scales similar to the length scale of the roughness. So that's not very useful if you want to do a large-scale experiment with a bunch of syrup, try to generate some kind of appreciable slip. You can't do that, and that's why this experiment didn't work with a syrup flowing over such a special surface. So we need to think a bit further. Another idea could be just lubricating the thing from the bottom with some fluid. And then there's a question of what kind of fluid? Well, okay, in nature, till has some kind of rheology. And actually, there's so much discussion about the rheology. Like, what is it? People on various scales reach different conclusions. On very small scales, if you run experiments, just take a bunch of till into your lab, shear it, and figure out its rheology. People come to the conclusion it behaves like a plastic material. But on larger scales, observational studies and inverse problems seem to suggest that till is more, that the rheology of till is more linear. So maybe something in between. A good compromise could be a viscoplastic rheology. So something like mayonnaise or syrup. Sorry, I can't stand there. Something like mayonnaise or syrup. But even for a first try, something Newtonian would be a good thing to try out first. And the very last idea could be, well, you could try flowing your syrup over a saturated granular suspension or a granular till. You would get some sliding there, but I would think not very much. So anyway, so those are three ideas. We're gonna start by looking at the second, because first didn't give us much slip. Let's look at the second. So if we look at the second, here's some bit of history that some of you in the audience could have remembered. You can generate appreciable sliding, so appreciable accelerations in your velocities, and by injecting a less viscous fluid under a more viscous fluid, you get something. In particular, you're seeing at the top here a viscous gravity current, syrup on top, and another viscous gravity current beneath it, lubricating your syrup. The viscous gravity current beneath it is less viscous, and because it's less viscous, it serves as a lubricant. And the region is split into two. The lubricated region is nice and long and flat. It's nice and lubricated. So we're happy that we're getting larger velocities in that region, and we can happily match it to our predictions and be really happy about it. But what happens is at some point, you keep running the experiment, you run into this. You run into some kind of new type of viscous fingering instability. So what is this instability? It's something that kind of, it kind of reminds you of Saffman-Taylor, but it's not really Saffman-Taylor because this isn't in a porous medium. This is a free surface flow. So we're not using Darcy's law. It's just free surface flow, and we're still seeing viscous fingering, and it's induced by a viscosity contrast. It's such a shame that this photograph here, you can't really see it very well on the board, but there are lobes. I hope you can see them. And you can reproduce these experiments many times, run a lot of them, just to see what kind of patterns you get and how you can control the instability. I'm really upset about the lighting in this one picture. It would have been such a beautiful thing to hang in my office, but unfortunately, it's only one of the lights came on, and it was the best experiment yet. It accents the complexity of the fingering patterns that you can get. Another group ran very similar experiments on a very similar setup, but instead used non-Newtonian fluids. And what they've done is they ran the experiments for long enough, or they've engineered it in such a way that that there were 4 major fingers, and they've ran it for long enough that the fingers themselves reached the leading edge of the syrup and overtook it. And the group have been comparing these types of lubricated flows to ice streams. So these very well lubricated parts of ice that we've seen in the movie and in the video of Antarctic ice velocities, they were in blue and purple colors and pink. Okay, but let's focus on the instability. Where does it come from, and how is it different to Saffman-Taylor? Because there's a similarity between Saffman-Taylor and this one. The obvious differences are one's in a porous medium and the other isn't. So a very simple example of a porous medium is a narrow gap between 2 parallel plates, like the thing drawn on the slide. In Saffman-Taylor fingering, when you inject a less viscous fluid into a more viscous fluid between 2 parallel plates, you get a fingering pattern, and you get a very similar thing in our case, but without the top plate. So you can imagine that we're like an analog of that, but without the top plate. And again, we can't use Darcy's law equation, Darcy's law again, for us. It's all free surface. So those are the main differences. But we still get a fingering instability, and it still occurs when you're injecting a less viscous fluid into a more viscous fluid, and it doesn't occur in the opposite scenario when you're injecting more viscous into less viscous. So that's a similarity. So because of that similarity, when we were thinking of naming this new instability, we thought about, okay, let's keep some kind of Saffman-Taylor name attached to it. Another name for Saffman-Taylor is viscous fingering, just that. So let's just keep that and attach non-porous to it. So in the end, we've settled on non-porous viscous fingering instabilities to describe this, this phenomenon. But if you have any better ideas than that, than non-porous viscous fingering, then you can tell me, and I'd be happy to reconsider. But so far, that's what we've settled on. Okay, so now we want to understand this instability, and to understand it, we need to first look at the basic state. When we look at the basic state, we can actually, the instability originates at the intrusion front, so we can simply just zoom in towards the intrusion front and look at what happens there. Asymptotically, there's a cube root singularity, and there's a parameter. There's actually 2 parameters, m and d in the denominator. What is m and what is d? M is the viscosity ratio, and d is the density difference between the 2 fluids. And since d is in the denominator, that means when you take your density difference to be smaller and smaller, that means the the densities of the two layers are closer to each other, and closer to each other, we're getting steeper and steeper gradients. So we're getting small d's are here, and in the d = 0 limit, we're going to approach a sharp front. And actually, the sharp front is a lot easier to understand because the shock front solution doesn't involve any singularities at the front. We can do a linear stability analysis without having to worry about singularities messing things up. Another advantage of looking at the d = 0 limit is that the instability, the mechanism of instability is clearest there. So in particular, we can figure out that the instability, by looking at the growth rate, which is proportional to a jump in upper surface gradient across the lubrication front, by looking at that growth rate, we can figure out that the thing is stable if and only if the jump in upper surface gradient, the red thing, is positive. And that occurs if and only if the viscosity ratio is less than 1. So as long as the density difference is 0, we're exactly in the Safman-Taylor case, that we are getting viscous fingering when we're intruding something less viscous into something more viscous. Exactly that. But the problem here is that the growth rate grows linearly with the wave number. And that is, so maybe let's skip to here. That is a problem because that means we have no large wave number stabilization. But same thing happened in Safman-Taylor. The very 1958 paper, the very first thing they did was this linear stability analysis, and the growth rate sigma was proportional to k. So they also had this linear thing, and to stabilize it, they added surface tension. That stabilized the thing. It turns out that we could add surface tension, of course, but we didn't because the two fluids in our problem were miscible. So we instead looked at what's going to happen if we relax the assumption that the density difference is 0. Relaxing that assumption provides a stabilizing mechanism, because then we're going to get the appearance of additional buoyancy forces near the nose, which stabilize the flow. So going back, we've seen that there's a similarity between the two, and the difference, apart from just the geometry, is that one of these is driven by a jump in dynamic pressure gradient, and the other is driven by a jump in hydrostatic pressure gradient. So there's always a pressure gradient driving the flow in both scenarios. In the Safman-Taylor case, the pressure gradient is dynamic because you're pumping things in from the side, and here it's hydrostatic because everything flows under gravity. Okay, so that's the main difference between the two instabilities, the main difference in the mechanism. And you can go and look at the regions of stability and instability. You can see that when your viscosity ratio m is large enough, you're getting a larger band of unstable wave numbers, and you can completely suppress it when you take your viscosity ratio to be smaller. If your density difference would be 0, that curve would be a straight line right here going up. But density differences stabilize things. And they stabilize things sufficiently that when the density difference is large enough, so 4, for example, then you don't have any of these instabilities at all. So you suppress everything. But 4 is a bit extreme. You can't really, I haven't found any fluids that give you such a large density difference. Most experiments are somewhere here in that region. So in any case, we've already very accidentally stumbled upon this instability. That instability messed up our experiments. We couldn't have any slip because of it. But on the other hand, it's interesting in its own right. So we had a thought, where else could such an instability possibly exist? And thinking, it has been suggested to me, after talking to lots of people, that it also occurs in nasal drug delivery and nasal drug and vaccine delivery. How does it occur there? So your nasal passages, they're coated with mucus. And so that's like one layer of fluid in your nasal passages on a substrate. And then when you deliver a nasal drug or vaccine, that's like layer number 2. And that layer number 2 is usually less viscous. So instead of injecting your fluid from below, you're now injecting the fluid, the nasal drug, on top of a pre-wetted substrate coated with mucus. This phenomenon of viscous fingering has actually been seen before our experiments on this new type of instability by this group, or maybe not before, around the same time, by a group of people in medicine who's been doing similar experiments, but the other way around, putting drug solution on synthetic mucus and looking how it fingers. And they call this phenomenon, they don't even know anything about fluid mechanics. They don't call it viscous fingering. They don't know what fingering is. They call it nasal dripping. So what is this nasal dripping and why do people care about it? Nasal dripping messes up nasal drug delivery, nasal vaccine delivery. How? Well, there has been this COVID vaccine trial that was for an intranasal delivery, and by AstraZeneca recently, and it was not successful. They abandoned it because the reason was that they couldn't estimate reliably how much of the drug was absorbed by the body and how much was eliminated through this nasal dripping towards the this digestive tract. So different patients responded differently. Like you couldn't estimate how much of that drug is actually just going to stay and how much the patient will just swallow it because it will drip along their nasal passages. And the difference between the patients is that some patients have a higher viscosity mucus than others. In particular, when you're in a diseased state, your mucus is of higher viscosity. So a diseased patient, when they get this nasal drug delivered to them or nasal vaccine, they're more likely to have nasal dripping or this finger forming, this non-porous viscous finger forming in their nose, which then makes the drug disappear faster and be not absorbed by the system. So yes, so this is something that people are concerned and can't really measure very well in this setting. So, okay, let's look at that setting. Let's see what the difference is. So instead of injecting the fluid from below, let's think of injecting it from above. And let's see what we can get. So again, we can predict probably the mechanism is similar. And we can also look at the basic state. This time the nose has a square root singularity. It's a bit different, but still you can get it out asymptotically. And this is something one of my PhD students was doing, and he produced these figures for looking at when the flow is stable and when it's unstable. So he did a linear stability analysis and looked at the growth rates, sigma. It turns out that these flows do get unstable, but you need your viscosity ratio, M, to be large enough. But it has to be like really large. It has to be over 180, the viscosity ratio. And for those viscosity ratios, you get, and the higher you go up from about 180, the bigger the band of unstable wave numbers. And again, you can stabilize things with a density difference. So if you are above a certain density difference, you can get rid of all these instabilities. So it could have been enough just to tell those people doing these nasal dripping experiments or these vaccines that they've been trying to deliver, just tell them to increase the density difference. Yeah. So that was a very big digression from the point. So the point was we wanted to generate slip, and we were faced just completely by accident with this fingering instability, which turned out to be pretty interesting and a new thing that was interesting in its own right and has applications to other fields. But let's go back to the main topic. How can we still generate slip in the lab without instabilities happening? And we want it to be appreciable, not just this tiny little thing that you can get with hydrophobic surfaces that you can buy. So let's go back to think about how we can do it. Let's go back to how these hydrophobic surfaces work and why they fail. So the no-slip surfaces, like this table, they're nice and smooth. You get no slip. But to obtain slip, you need some kind of cavities, and the cavities need to be pre-filled with some kind of liquid or gas, and then the fluid, rather than flowing over a mostly solid substrate, instead flows over a liquid or a gas, which then generates sliding. And that failed when the cavities were really small, like these manufactured things that they've been using in these microfluidic applications, the super hydrophobic surfaces. But what if we let that spacing be a bit larger? What if we make it like appreciably larger, like a centimeter? Then of course, we need to pre-fill it with some kind of fluid. It can't just be gas or your syrup will flow into the interstices. But let's pre-fill it with some fluid and see what happens. So we pre-filled it, or theoretically looked at a thin film of viscous fluid flowing over such a structured substrate, pre-filled with less viscous fluid. In the interstices, the structured substrate consists of cavities, a sequence of larger cavities now. And the cavities, if you zoom into one of the cavities, you'll get this box right here. What's happening in the box? So the top fluid, the viscous gravity current in dark blue, exerts a shear stress on each cavity. And that shear stress then drives the return flow within each cavity. And then from that, you can find out what the flow field is. And in particular, you can find out that there is a non-zero sliding velocity in red. And we're going to call it UI for now. So we have a non-zero sliding velocity. That's what we wanted. We wanted a non-zero velocity right there at the bottom. And that's what we're getting with this. And now we can kind of control it because we can get an expression for it. We'd like that velocity to be as big as possible. So what is that velocity? That velocity, you can write it as some kind of function of x, where x is that coordinate here. It has an approximate form like that. You can get that after just doing some numerical simulations and fitting a curve to the simulations. So you get approximately that. But the important thing about it is that it's proportional to the shear stress S. So the shear stress exerted by the upper layer. So keep that in mind. Everything else there is just X and constants. But what's the thing that we need to care about now? So the top layer, actually, it doesn't really care about all the inhomogeneities of the substrate. Sure, the substrate does involve larger cavities now than usual, but we're still assuming that they're much smaller than the whole length scale of the viscous gravity current. So the whole viscous gravity current, the dark blue, doesn't really care about all those small scale inhomogeneities. All it cares about is an effective sliding at the bottom, or an average sliding velocity at the bottom. So that's what we're going to do. We're going to average out over all the inhomogeneities and obtain an average velocity. That's that thing, the angle brackets denote an average velocity at the interface. And that average velocity, you can obtain some expression for it in terms of S, and you can evaluate what S is. S, the shear stress for any viscous gravity current, single layer viscous gravity current, you can evaluate what it is, plug in the formula for it. In the end, you're going to get something in terms of the thickness of the blue fluid, dark blue fluid, and its upper surface gradient. And there's one thing in there, this parameter lambda. That lambda turns out to be important. It's a so-called slip length. It's proportional to the ratio of viscosities between the two layers. So what does that mean? That means that when your lambda, the ratio of the viscosities between the two layers is large, then you're going to be ending up with a large slip length or a very slippery substrate. And that's good, that's what we wanted. So we can control the amount of slip by controlling the viscosity in each cavity. Viscosity of the fluid infiltrating each cavity. And intuitively, when you're going to saturate your substrate with a very low viscosity fluid, that will produce a large lambda, large viscosity ratio. So that's very intuitive. All we have to do is to infiltrate your substrate, saturate your substrate with a low viscosity fluid to get appreciable slip. And what you can do is you can use that expression that we just found for the velocity. You can use it to obtain a depth average flux. So you can use lubrication theory, obtain your usual flux of viscous fluid, which contains the usual term, the 1/3 times h cubed times something. That's the usual term for things that spread over a no-slip surface, plus the thing involving the lambda. That's all that contains. The thing involving the lambda, the term involving lambda, contains all the slip that there is. And that's what we get. But it turns out that you could have, rather than going through all the pain of looking at what happens in each cavity and then averaging it all out and seeing what you get, you could have instead just applied the Navier slip condition, that U is lambda du by dz at z equals 0. And that will give you exactly the same result. What does that mean? That means that our substrate on the large scale obeys the Navier slip condition. So that means our substrate is slippery with a slip length lambda. How beautiful. That means we can actually control slip. We can actually have slip, we can control it. The slip length will be just something in terms of the viscosity ratio, 0.1 times the viscosity ratio. Okay, so let's test this. Let's see if it works. So I had a summer student working on this at some point, doing these experiments, viscous gravity current like usual, but this time flowing over a saturated substrate consisting of a sequence of periodic two-dimensional cavities or cells. They were pre-filled with a less viscous fluid, or it could also be the same viscosity fluid. He also did an experiment like that. And what did he get? So these are some pictures. When the viscosity ratio is about 1, so for example, when he uses the same fluid in the substrate as the viscous gravity current, just saturate it with the same thing. You get some slip, a little bit of slip, but not very much. It looks pretty similar to what you would expect over a no-slip substrate. You start getting larger differences, so larger slip lengths and higher velocities for viscosity ratios of about 13, say. They're nice and appreciable then. But there is a limit to this. You can't keep going with your viscosity ratios because at some point you're going to hit this barrier that your the lower layer itself, you start getting a long wave interfacial instability at the interface. So you have to stop around M is 95. So M is order 100. You have to kind of be careful, and you can't increase it much after that because you start getting these long wave instabilities. And you can compare all this to the theory, and here what we're doing is all of it is collapsing on one curve because you can non-dimensionalize things. And these are the very slippery and the no-slip experiments, all on or close to no-slip experiments on the curve. So yeah, I've been talking a lot. So what have we done? We've tried to generate slip, kind of were successful for early times, and then ran into a viscous fingering instability, which set us back a little. But nevertheless, the viscous fingering instability turned out to be quite interesting and also useful in other fields. The viscous fingering instability happens to be similar to Saffman-Taylor, so we've used that similarity to name it the non-porous viscous fingering instability to accent the fact that it's a viscous fingering instability, but it occurs in not in porous media. We've also found that you can, going back to the original goal, how do we introduce slip? We can introduce it by blowing up the lotus leaf to larger scales and having a substrate consisting of larger scale cavities. That will still give rise to Navier slip, and you can control the slip length by controlling the viscosity ratio, which is convenient. But I should say the experiments are messy, so you have to think if it's worth, if you want to introduce slip in the lab, is it worth doing this or is it too messy? I want to just end with this. So I'm looking for a postdoc. If anyone has any PhD students who are ending, or if you are a PhD student who's ending or looking for a job and are interested in viscous fingering, then you can shoot me an email and we can talk about more details.